scattering amplitudes at large multiplicity.
Okay, well, thank you so much for having me. So today I'm going to be telling you about some work still in progress together with Nima, Alfredo, Song, and Xiang about what happens when we scatter a very large number of particles. So this large little n here, this little n stands for the number of particles. And this is a limit where in the standard way we think about amplitudes perturbatively. It seems to be particularly hard to control what's happening because the number of diagrams becomes very, very large. Nothing simple seems to be happening. But what we find is that actually the answer becomes remarkably simple at infinite n. Okay, so anyway, so that's what I'll be talking about today. And so the plan of the talk is the following.
In the picture, it looked like 2 to n or n to 2. Did you mean that specifically, or you just didn't bother to?
Oh yeah, I will not be, yeah, you can, defining who's incoming and who's outgoing is something about defining exactly some features of the kinematics, which, yeah, so, yeah. As I'll explain, I'll be describing fairly general kinematics, which then you can specify to exactly the regime you want. But there's a large number of particles involved in the scattering process, whether you think of it as 2 to n or n to n. Both will be captured by what I'll describe. Anyway, so we're gonna, in the first part, I'll start by just defining the problem, exactly what scattering I'll be talking about, and in particular, what are the kinematics that we'll be considering as we send n to infinity. And this is all gonna be for this very simple toy model theory of scalars, traced by cube theory, which I'll also describe in a second. And then I'll immediately jump into some sample results of what the final answer looks like. So this part will be a little bit unmotivated, but it's just so that you see how strikingly simple the formulas are. And the main aspect, which really sort of challenges the naive expectation that we would have, is that we see that as we move around in kinematic space, the answer sort of jumps. The formulas that we get sort of jump in an interesting way. And then the third part, basically, I'll explain how we derive the results from this part two. And this is all using this new representation for these amplitudes that go by the name of tropical integrals, or equivalently, they're also called global Schwinger parameterizations. I'll explain what all of this means. And there I'll already sort of hint that the reason why we can control this limit is because these integrals suggest an intimate connection to a sort of a statistical mechanical problem of random walks, that the amplitude can be interpreted in this way. Anyway, so this by itself could already be a 1-hour talk. But we're extremely excited about this fourth part, which is really that starting from these sort of tropical integrals, we can do some manipulations that then let us find a new representation for the amplitude that really makes manifest that there's a dual theory for any n, where really is just describing sort of the path integral for a particle moving on a half line. Okay, and this last formulation is the one that makes it extremely simple to derive what happens at infinite n. So this is mainly going to be a summary in the last part, but I hope you'll, I hope you'll still be happy to hear it. Anyway. Okay, so let's get started. So this theory that I'll be talking about is this trace phi cube theory. So there's a kinetic term and a mass term, and it has a cubic interaction. So these phi's are, the keywords are their scalars. They have cubic interaction with their colors, so they're n by n matrices. Anyway, and at tree level, this means that once I fix the color ordering of the external states, then I only have contributions from planar graphs. Okay, so at 4 points, that would mean I would only have the S channel and the T channel. And today we'll be solely focusing on the tree level case. And we're always going to be assuming that these capital N, so the number of colors, is strictly larger than little n, precisely so that when I fix the color ordering, I only get contributions from planar graphs. Okay. So in general, when we describe amplitudes perturbatively, there are two integers that play a role. One of them is the loop number, the other one is the number of particles. And of course, the physics of large loops is interesting as it's related with what happens at strong coupling. But the two limits are intimately related via cuts, right? If I start with a high loop diagram but with no external legs, I can cut the loop propagators down all the way until I get a pure tree diagram. And even this part, which is just a tree diagram, is what's called a leading singularity, and it plays a significant part of even the sort of higher loop answer. Okay, so we can sort of go down this plot via cuts. But in general, when we think about different scattering processes that we can consider, it's clear that, 2-to-2 scattering, or even if we want to learn something that's happening at strong coupling, we have that, of course, 2-to-2 scattering, even though it's dominating at weak coupling, it is exponentially tiny at strong coupling, while the opposite holds for the case of n-to-n. So at strong coupling, the things that will mostly be happening is processes that involve a large number of particles. So in particular, since I'm talking about a color theory, there could be the naive expectation that in the strong coupling regime, I see the emergence of some sort of dual description. And of course, the regime where we would see more transparently the emergence of this dual description, which would be both at large loop and large little n. But today we're going to sort of make a warm-up on that, sort of starting to see that there is already some simplicity emerging, even in the weakly coupled regime, where we just make n large. Okay. Anyway, so let's see, from the standard approach, how we could even access these, and what are the limitations in accessing this limit. So from the summing over Feynman diagrams clearly becomes hopeless, because the number of diagrams grows exponentially with n, like for the n. But we can avoid this exponential growth by using recursion relations, which basically just repackage the amplitude and write it as sums of products of lower point amplitudes. Okay, these are called the Behrens-Euler recursion relations, which are just a reflection of the classical equations of motion. Okay, so the way we make progress in these plots is we can go up in the n-axis by gluing lower point amplitudes, and then potentially up in the loop direction by using cuts. Okay, but what I'll talk about today is something different, because clearly if we glue, then to know what happens at an even larger n, we always need to know the one before. So what we want to find is really some formula that computes the amplitude directly in the n equals infinity limit. Okay? And so one final piece of motivation, or a question that one could ask, is why am I studying this theory? Why trace phi cube theory? Well, over the past few years, there have been many developments in new ways of formulating the amplitudes for this particular theory. All of them really come from a new way of thinking about open string amplitudes, in which, in the sort of field theory limit, these integrals sort of spit out a new representation for the field theory amplitude. And this is what's called this global Schwinger representation, which I'll describe a little bit later, and it's crucial to sort of make this analysis. But more generally, we've also seen that this seemingly toy model theory actually is connected with other theories that we care more about. In particular, we can obtain the amplitudes of pions and gluons by a simple sort of kinematic deformation. And at the end of the talk, I'll even mention that some of the results that I derive for large n scattering for these scalars actually generalize to large n scattering of pions.
But your capital N, do you keep it also large?
Yeah, the capital N needs to be strictly larger than the little n, so that I can talk about a color ordered amplitude.
So you talk about so you work on the planar limit.
At true level, yeah, at true level, it's not about being the planar limit. It's just, I'm not sending, it doesn't need to, the ratio doesn't need to be going to infinity or anything. It just needs to be strictly larger. Like at loop level, if I did a similar analysis, I could also analyze what happens for non-planar diagrams. It's just that at true level, when you fix the color ordering, there are only planar diagrams. That's all. Anyway, and even beyond the context of scattering amplitudes, a lot has also been understood for the sort of flat space and cosmological wave functions, and some of the results that I'll show also generalize to these contexts. Okay, so before I start, I would like to make one final side comment, which is a question that I frequently get when I talk about this, which is whether if at large n, the physics that I get is becoming classical in any sense. And the sort of first important point is that we will not be talking about the scattering of coherent states. So we're all familiar with the fact that if I have a classical wave that has a large amplitude, this is described by a configuration that has a very large occupation number, so many particles with the same momentum. That's what we call a coherent state. And that's not what I'll be talking about today. Instead, we're interested in the situation where it's completely general and there are n distinct momenta, okay? And another obvious connection is that we know that true level amplitudes are related or are equivalent in a sense to the classical solutions of the equations of motion. In particular, if I have, say, n incoming waves described by some plane waves, then when I evolve the classical equations of motion, there will be a piece of the solution where there's a single outcoming wave whose momentum is equal to the sum of the incoming ones. And the coefficient of this piece is precisely the true level amplitude that I'll be describing. And in particular, relating with the classical equations of motion was something that in the 90s, Voloshin studied to understand what happens at very large n, but crucially, he was studying what happens when all the particles are on threshold. And so in this case, the physics becomes effectively one-dimensional, so the classical equations of motion simplify dramatically, and that's why he could sort of attack this problem.
Related to this fact, because there was Voloshin and then Rubakov and Son and Geniakov,
Exactly.
a lot of people, and they were also, I mean, they had a method also to deal with few quanta in the initial state, right? Because they started working with coherent states, then put a parameter alpha in front of the coherent state, took the derivative with respect to alpha, and then sent alpha to 0. And results seem to be, at least in the regime where they could control it, they made sense. So,
but so in that case, probably still a situation where you're getting a very
It's close to one dimension.
It's close to
right?
one dimension. You probably have many particles that probably will all share
You mean
the
because they
same
are
momentum.
threshold?
Exactly.
But they were in general, but they were studying, like they didn't have like capital N, they were just studying 2 to n.
Yeah,
like
they were
in
just
five-
doing
in
uncolored.
And it is
five
also
plus
uncolored. Yeah. So
Right.
that is a difference for sure. Yeah, that is just in phi cube theory.
But
So-
I think just broadly that there are situations where at any end the physics simplifies. It doesn't have to go to large n. At any end it simplifies if you go on threshold. Then you can analyze it in some way, and you can take n to infinity. So, well,
But they were
She'll say,
they were not
yeah,
restricted to threshold. They were literally kind of.
but I think not everyone are going off in random directions. That's
Yeah, I think-
that's
Well, they were just
I
asking
don't
the
know
question
if
like
this
2
is
to n cross section, how it behaves at large n, and they were getting it given by semi-classical answer. Similar to what Ricardo is doing now with calculate, but actually that's kind of.
So indeed, the question is, does that require to have, if not particles at threshold, many particles
I think-
close
I think-
by?
I think
I
it
think
requires
so,
many
because that's a
particles close
coherence,
by,
like,
yeah.
because as you're saying, I think, well, I am not 100% sure. But if what they're doing is something close to a coherent state, then
Well,
just
the
by
initial state
definition,
was just 2 particles. And just
And they had this trick of writing
Yeah,
it as
they
a
had the
coherent
trick,
state, then
but-
taking derivatives and sending the coherent amplitude.
Yeah, I think if it's
But-
close to a coherent state, it's not what we're.
anyway, there should be a limit of what we're doing, which would resemble like a coherent state, because we can then sort of specialize to the case where all the momenta, or many subsets of momenta are the same. But here the point is that we really want to understand the generic function that we get for completely general momenta.
Yeah,
And
and
yes.
maybe the question, again, it's related to what you said at the beginning. They had, of course, finite n, 2, 3, capital N, and large little n.
Yes.
And
Little n is the number of particles.
little n is the
Little n
number
is
of
the number of
particles, large n
particles.
is the number of
N and
columns.
M, maybe?
So, and here I still don't understand why it's so important that capital N is larger than the number of particles.
Yeah, and the main reason is just because the representation that we have at the moment that will let us understand what happens at large n only holds for like the situation where there's just a plane. We don't have to account for like also the non-planar diagrams.
But it has anything to do with the fact that you don't want a coherent state? Or you are
No, it does not have anything to do with that. It's just that the method we have to study the limit holds for the sort of classes of diagrams that are compatible with a particular ordering, right? And
Basically, there's going to be some, as you'll see, there's going to be some kind of smoothness a requirement on the kinematics that we're talking about. But what qualifies as smooth? What qualifies as smooth is that since you have a color ordering, the momentum for 1 is not far from momentum for 2, not far from momentum for 3, and so on. So there's something smooth.
Yeah,
If you
so-
didn't have, if all orderings were there, then there's nothing smooth. You have to sum over.
But that's interesting whether the semi-classics would apply in this regime, because it could be that these conditions that capital N is larger than little n would contradict to the applicability. But yeah.
But since they do uncolored, there's not particularly.
And the particles are in the fundamental, I mean, the
They're-
capital N is like color and the large N limit, right? That's what you're,
So these scales would be in the adjoint of like some
everybody's.
SUN.
Scale
Because
glue.
for that the whole point was that they wanted to apply it not to coherent states. They were saying no, because naively semi-classic applies to coherent states, but even for 2 particles you can get the correct result for 2 to n by
I see.
right.
Yeah. Yeah, so, but there the n may have been, I don't know if there was something hidden that said that.
I mean,
this n
I
is
suspect since they were
semi-coherent.
close to the phi cube theory rather than the trace phi cube theory, then this then it makes a huge difference. The capital N is bigger than little n or
Right.
the other
So
way.
it could be that
Yeah,
this.
Are you going to explain that? Because to me, it's not obvious yet.
Yeah, I'll explain this aspect of the smoothness. Sorry. Anyway, so but what I want to say with this is just that the classical equations of motion for sure contain the object that we'll be studying, but at the moment it is not clear how we could use it to sort of draw the conclusions that we'll be drawing. That's all. Okay, so let's proceed. So if I have an n-point amplitude and I have an ordered, color-ordered amplitude, then if I list the momentum of each particle on the scattering process tip to toe according to this color ordering, I get this closed polygon. Okay, just because of momentum conservation, because the sum of the momentum has to add up to 0. Okay, so and in particular, we have that for the planar diagrams that we'll be considering, the singularity, so the location where these tree-level amplitudes have poles, are exactly when sums of adjacent momenta go on shell. And these particular sums of adjacent momenta are nicely captured by the sort of length squared of chords of this polygon. Okay, so I'll define these variables xij to be exactly the length squared of the chord going from vertex I to vertex j, and that is shifted by m squared so that the singularities happen when these xij's go to 0. Okay, so this is just how I'm going to define my kinematics. And in particular, we can list all the possible cubic diagrams that contribute to this amplitude by considering all the possible triangulations of this polygon. Okay, so for example, here's a triangulation. It's a collection of chords that divides a polygon into triangles, and I can obtain the dual cubic graph by drawing a cubic interaction inside each triangle. And then the contribution that I get from this diagram to the full amplitude is simply 1 over the product of the xij's that I associate with each chord that I see on the triangulation. Okay, so this is just rephrasing things that...
Sorry, what is an x?
Is this the variable that I just defined a second ago? The sum of the momenta...
The four.
Yeah, exactly. So it's an invariant. It's a Mendel semi-invariant shifted by this mass square of my particles. Okay, so it's the length squared of this chord.
In the mostly plosimetric.
Yeah, it's mostly plosimetric, exactly. So anyway, so for example, anyway, these are exactly, these precisely capture the momentum flowing through the propagators that are dual to the chord. Okay, so that this is just a contribution we get from this diagram. Okay, so then in this way we can think of the amplitude as a function of these xij's, and which is given by the sum over all the possible triangulations, where for each triangulation I get one such factor, okay? And I'll also be assuming for simplicity, for now this does not have to be the case in general, that the momentum live in sufficiently high dimensions such that I don't have to care about relations between the xij's, okay? You can input them at the end of the day. This is just to simplify the analysis now. Okay, so to keep track of the kinematics, so my function as data receives these variables xij, which are labeled by 2 indices. So we're going to keep track of all of them by drawing them in a grid, okay? So anyway, we draw this grid with this 45-degree angle, just for historical reasons, not any deep thing at the moment. So any point here labels one of the xij's, and when I move along this direction, I increase j, and along this direction, I increase I. Okay, such that each point inside here is a chord, and the points on the boundary are different in the sense that they're associated with the edges of the polygon that don't enter on the amplitude, so they're not variables, so we should not really think of them as variables of this mesh. Okay?
Could you just read the word on this going vertically, something or other a sub
Don't
n?
enter an, that's all. I'm saying that these variables here on the left boundary, this that I marked in green,
They
don't
go
enter
into
the
the side.
amplitude. So that's why they're not to be considered as the variables that we care about are those that live in the middle. That's what I'm trying to emphasize there.
Sorry, so this already requires that capital N larger than small n?
No, this is just about kinematics. This does not require any of that. That's a statement about the piece that we're computing of the amplitude is something meaningful. If you have capital N smaller than little n, there's no meaning in a color ordering.
Right, no, that's what I'm trying
That's
to
all.
understand. But
So these are just the kinematics that are when I draw the polygon where I have an ordering, right? The xij, of course, depends on knowing the underlying ordering, right? Like, if I didn't have that, then it wouldn't make sense for me to draw this momentum sort of in this particular way. This would not be the singularities of they would be part of the singularities, but they would not capture all of the singularities. these xij's.
No, that's what I'm trying to ask. So
That is true. So if I did not have capital N strictly larger than little n, I mean, there's not a notion of like, I mean, you would also get contributions from diagrams which are non-planar, and then you would also have singularities that involve dot products of momenta that are not adjacent. I mean, it doesn't even make sense to talk about adjacent anymore. Like that's the whole point.
Adjacent is adjacent in color.
In color.
No, I understand, but I'm just trying to, because clearly at capital N equal 1, we have no notion of it whatsoever, right? But at capital N equal 2,
You need capital N bigger than little n strictly.
Yeah.
I mean, let me say it another way. You're familiar with the fact that for any capital N, there's a trace decomposition, right? But you have to sum over all the traces, okay? So if you fix a set of colors, and the number of colors is less than n, then many traces will contribute to that particular set of colors, like n equals 2, right? N equals 2, capital N equals 2, little n equals a million. You're going to have to sum over zillions and zillions of orderings, right? This story is about something simple that happens for a given color ordering. Now, that given color ordering is a meaningful thing at any capital N. I mean, it's a mathematical thing at any capital N. But for the amplitude itself, you have to sum over many different orderings. As soon as capital N is bigger than little n, then there is a color ordering for which what we're talking about is the full amplitude. So we always imagine that capital N is big enough if you want to interpret it directly as the amplitude, rather than as a piece of a decomposition of the...
so what happens when little n is larger, then you need to add contributions from different...
Yes, right.
Different
But at the moment little n becomes larger than capital N,
Right.
the point is if you have a million particles but 2 colors, there's millions of color orderings at color 1, color 2, 2, 1, 1, 2, 2.
And
You have to sum over
it's
all.
not really just
Right.
some, because there are some trace relations.
Exactly. Yeah, then
Yeah.
there's a whole story,
Right,
there's a basis, blah, 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 but yes.
And why do you want the particles to be in the adjoint instead of the fundamental? If I understood what you said, that's what you're using.
Because otherwise there is no notion of adjacency. Right? I mean, you don't have 2 lines, but just one.
Yeah, exactly. There's like
And
double
then
line.
you
If you draw the I mean, everything that is being said is really very easily captured by the fact that you have these scalars that have 2 colors. Or anyway, the sort of thing that I'm computing is some expectation value,
Now I see. Thanks,
or
Marcel.
like C1. Anyway, and the thing is that if I have more colors than n, when I draw them like this, they're sort of, the only way I can fill in the graph is like sort of things that are planar diagrams in the middle. If they are repeated, then I can contract them in different ways. That's all. Okay. So the question that we want to ask, this is now the notion of smooth kinematics that Nima was mentioning a second ago, is we want to ask what happens to the amplitude when we let a smooth function, x of u and v, live on the mesh from which we read off these kinematics xij. Okay, so that then in the large n limit is like we're just sort of discretizing this mesh finer and finer. Okay, so that's the question. And it turns out that for this analysis, on top of the xij's, another variable that will play a role, and it will be clear in a second, is these sort of discrete double derivatives that we can associate with each internal square in the mesh. Okay, so this is just some discrete double derivative of the function that we define on the mesh. Okay, so to each little square we associate a Cij. Anyway, so a particular linear combination of these x's. And one important aspect which will be relevant in a second is that while theCij's that correspond to little squares in the middle of the mesh will all be of order 1 over n squared, because they're double derivatives, those that live in the boundary of the mesh and that touch these variables that are not part of our analysis will end up being of order 1. Okay, so I'm going to give an example in a second that will make this clear, the distinction between the two. But these will be other variables that will be important in the analysis. So let's look at the simplest possible configuration. So this is the case where the profile that I pick is a constant. Say they're all equal to m squared, or let's work in units where m squared is 1. So let's say all the x's is equal to 1. Then the amplitude just turns into a pure counting of cubic diagrams. Okay, so that's the same as a sort of 0 external momentum limit, or equivalently where this theory becomes a matrix model. Okay, so before proceeding to the answer, let's see what here when I put this function on the mesh, each single point gets a 1. And so we see that the middle c's all are equal to 0, but the boundary c's remain equal to 1. Okay, so this is sort of the distinction between these different discrete double derivatives that I introduced. Okay, so in this limit, it's just diagram counting, and this number of cubic planar trees is given by these Catalan numbers, which have a well-known asymptotic expansion at large n. So at leading order, they grow like 4 to the n. This is the exponential growth of the diagrams. And then there are subleading corrections. It's n to the 3/2, square root of pi, and so on. Okay, so this is the sort of a limit where we know what the amplitude does at large n. So the question that we want to ask to begin with is really what happens to these factors, these log 4, so the leading behavior in n, as we turn on a smoothly varying function in the mesh. Okay, so we expect that it will be corrected to some function that will, of course, depend on the profile that we pick. So we want to know what does the log of the amplitude over n asymptote to at large n. Okay, and this assumption of these smooth kinematics is basically telling us that it's not like there's a particular class of diagrams that is dominating. Instead, what's happening is that the sum over all diagrams is smoothing out in some way. Okay, so that's what we want to study. So again, just for another picture to keep in mind, asking for a smooth function on the mesh is completely equivalent to saying that I read off my momentum polygon from some smooth underlying curve. For example, here I could think that the octagon that we had previously was inscribed in some particular curve, and I defined the large n limit by saying that I point down more and more points on this curve following some particular distribution, with the curve sort of remaining fixed. Okay, this gives rise to what we call smooth kinematics. And other possible configurations, one that is kind of physical and that fits within the sort of kinematics that we'll be studying today, is something analogous to like a bomb going off, where there's a particle that has a large momentum, and then it sort of decays into many, many particles that have a small momentum. Okay, so this is one particular situation which will be captured by the regimes, the sort of subsets of kinematic space that I'll describe in a second. Okay, so having defined the problem, let me now jump immediately to show you what the amplitude looks like at infinite n. And so now to do that, I'm going to have to define a few variables that are going to be even more unmotivated. So hopefully you'll stick with me for now, and they will all have a natural, like they will all be motivated in a few slides. So I'm going to define these ak to just be the variables x1k. Okay, so the sort of distances anchored at point 1. In all of this story, we always need to pick some sort of underlying basis if you want. Here, there's a special point, which is this 1. And because of the cyclic symmetry of the amplitude, we can access the other regimes by using that. Okay, and then I'll also define these bk as being a particular c. So these ck minus 2 are those that live here in this end of the mesh, okay, minus x1k. So I drew these definitions here because they will appear on and on later. And then the c star is this other c that lives in this other end of the mesh, okay. So these are just the variables that the function will depend on. So for example, if we study a regime where all of the ak's are smaller than the bk, so this is a chunk of kinematic space, the claim is that at infinite n, the amplitude asymptotes to this very simple product of 1 over ak plus 1 over bk. Okay? This wiggly arrow just stands for that the log of an expression over n goes to log of the other one over n. So this is saying that the leading behavior in n that sits on the exponential is well described by this. Okay, so this is quite surprising. There are exponentially many diagrams that are collapsing into this single term. And there are other sort of funny features. One of them is the fact that this bk that we see here is not a pole of the amplitude. For any diagram does this enter as a pole. However, it enters in this sort of asymptotic expression. And it's completely fine because this expression is only valid in the regime where the b can never go to 0. So it's not a genuine pole. Okay, so the way that we check these answers is also, I mean, other than showing them, as I'll do a little bit later, you can also, in this simple scalar theory, actually compute the amplitudes on your computer using these recursion relations that I mentioned in the beginning, and that lets you go up to n of 1,000. And so here's like some example of some AK and BK profiles, so that AK is always smaller than the BK. And here on the right, it's the comparison between the log of the amplitude over n and the log of this A naught, which is this predicted product over n. So you see they're getting close where the offset is proportional to 1 over n. They look pretty close all the way through, but we started at n of 100. Okay, so this is why they already look pretty close.
And that holds for any capital N as soon as it's larger than.
As long as large n is greater than little n,
Right.
all of this will always hold.
Mhm.
Exactly. Okay, so then now, for example, another regime is when you say that instead AK is greater than the BK, but now this interesting ratio is smaller than 1 and increasing in K. Also not obvious why you should care of this interesting ratio. I'll get to that in a second. Anyways, this is one particular profile that satisfies these conditions. Now we claim that the amplitude asymptotes to this other very simple product of 4 over AK plus BK. Again, something which is not a pole of the amplitude. And here the comparison, now the corrections go like 1 over square root of n. Okay? Anyway, then there are other regimes, just so you get an idea. It's not always the case that I can write down a closed form. So if you look at exactly the same regime, but these ratios now decreasing with k, now it converges to this product where the AK and BK are shifted by the C star sigma bar, but now the sigma bar is the solution to some interesting equation that depends on AK and BK. Okay, so this is now all going to come out from our analysis, but this is already to see that the answer, depending on the region in kinematic space that we live in, sort of jumps and takes different characters. So this is now all going to come as a result of some analysis. Anyway, so this is just, again, the comparison with the numerical results for this last case. Okay, so now let me switch to talk a little bit about this new representation for the amplitude, which allow us to derive these formulas. So let's start with an extremely simple example where doing this is a little bit overkill, but even so, if I have 4 points, we know there are the S channel and the T channel, one of them 1 over x13 plus 1 over x24, and it's clear that I can Schwinger parameterize the S channel by writing it as an integral over the positive real line over some Schwinger parameter that I'm calling T13 here. And I can do the same thing for the T channel one. I can add another such integral. And now I can also easily combine them by defining the exponent of the original integral by this interesting max function. Okay, so now I have an integral that ranges from minus infinity to plus infinity, such that when T13 is positive, this max gives me 0, so I just have the Schwinger parameterization of the S channel. But when T13 is negative, precisely this coefficient fixes the exponent such that I get the Schwinger parameterization of the T channel. Okay, so not much has happened. So it's just a simple way of putting the two diagrams together. Now, at larger n, it's clear that I can also obviously Schwinger parameterize each diagram by writing it as an n-3 dimensional integral over the respective Schwinger parameters. But it is also obvious that if I now would like to glue all of these different integrals together to a sort of single space, the whole space, then the amount of work that I'll have to do this would be exponentially hard. It would be sort of as large as the number of diagrams, because I would need to do this one for each diagram. Now, the output that we get from this sort of different way, or new way of parameterizing the string amplitude, is that in the low energy limit, they precisely give us such an integral. Okay, so they'll give us this global Schwinger representation, but now the important point is that there's only a polynomial number of these max functions, but that divides the space into exponentially many different cones. Okay, so basically you have a polynomial number of these maxes that then gives you, in each different domain in T space, will give you the Schwinger parameterization of exponentially many different diagrams. Okay, and that's the sense in which you've gained something. Anyway, the reason why these are called tropical integrals is precisely just because they're made out of these max functions.
So,
Yes?
so you're claiming that surfaceology is telling you that there's only a polynomial number of the max diagrams, or did you somehow explain why there's only a polynomial number?
Oh, it comes as an output. You can show that it's a polynomial number of max functions. And you'll see, and the main reason is because each max function will always multiply one of these C's, okay? And you can count them that there's always a polynomial number of these C's. Okay, anyway, and this all comes, yeah. So I'm going to give you an example now of what this is. So the 4-point was pretty trivial. Nothing really was done, but I'm going to show you these integrals follow a very sort of recursive formula so that we can sort of write down what they look like in general in an easy way. I'm not deriving them now, but anyway, just to see what it looks like. So for example, at 6 points, I start by Schwinger parameterizing some diagram, which is why, the index 1 is special in my analysis. I started by Schwinger parameterizing the one containing the propagators that are called x1k. Okay, and now I extend the integration domain to the whole space, and I start adding these max functions. And the way that I add them is I start out by all of the c's that live in this boundary of the mesh, and each of them multiplies a max that involves 0 and one of the Schwinger parameters. Okay, so I have 3 of these guys. And then as I keep on going, I get that each c multiplies a more interesting max function. So in this next layer, the maxes intertwine 2 different of the integration variables in pairs, and they involve these nested sums. And finally, the last guy now has the most interesting max function, which involves all of the different integration variables. Okay, now the claim is that if you integrate this integral over the whole space, you get the sum over all of the different 14 diagrams at 6 points. Okay?
Just maybe to be clear, each one of those things, each one of the maxes is linear somewhere, right? I mean, obviously, for example, when T13 is positive, the C13 max is 0. When T13 is negative, the C13 max is negative T13, and so on. So each one of those terms has some domain in which it's linear. In fact, each term by itself kind of divides T space up into regions where it takes different linear factors. The remarkable claim of this business is that if you sort of overlay all of those regions on top of each other, you've divided the entire region into all the Feynman diagrams.
Yeah.
And that's the sort of specific sense. Here, still the numbers are not so dramatic, but there are 6 C's.
And there's 14
but there's 14 diagrams. Okay? And as you go higher and higher, there's always of order n choose 2 C's, just the n squared C's roughly, but there's order 4 to the n diagrams. And that's the essential magic of this business. At tree level, at all loop order, that's really the point, is that all the different possible diagrams and space-time processes are actually generated in this much, much more efficient way.
So how many dimensions, space-time dimensions, do you need to play this game? I mean, can you start with 0, for instance, and compare, say, with Bender,
Yeah.
Woods, Zenjusten, all the results?
If you're in 0 dimensions, essentially,
It's a
Carolina's
little
first
bit trivial,
example
but
is 0 dimensions just counting is just Catalan numbers. And
So
you
you're just
can.
specifying the x's and the c's to be something. These integrals hold in any number of dimensions. If you want to specify the kinematics at some particular fixed number of dimensions, that corresponds to just some choice of your x's and your c's, which you can input at the end of the day.
But indeed, in 0 dimensions, it's just diagram counting.
Yeah, that was-
And this is actually, I mean, physicists credit the famous paper 770s. It actually goes back to the mathematician Tate from the 1950s, who really counted all these diagrams. And indeed, this way of thinking is another way of counting those things. It's not quite related to the things that people care about in standard matrix models, because matrix models are interested in correlation functions of traces, of sort of UN invariant operators. Here we're looking at more things like amplitudes that have tons of color indices on them. And so we're having some fun at the Institute this semester trying to meld these two world views together. But,
Anyway, okay, so this is the representation of the amplitude that I will be dealing with, but in particular it actually will be even simpler than this, and it's precisely because, as I mentioned before, if we assume that we have these smooth kinematics, then we know that the internal C's are actually order 1 over n squared, while the boundary ones are still of order 1. So at leading order in n, if we only care about the leading behavior, we can just neglect them to begin with and deal with the simpler integral where we don't have them. There's a slight subtle thing here, which is the fact that, okay, they're 1 over n squared, but they're order n squared of them, so the effect could build up. Anyway, I'll talk about that briefly in the end, but for now, let's just throw them away. It is correct for most of the analysis at leading n. Okay, so then the integral that we have at general n takes this sort of simple form where, well, it's an n minus 3 dimensional integral, and there's a piece where all of the integration variables are decoupled, right, which involve the simpler set of maxes that have just 0 and a t. Okay, so those are proportional to the c's that live in this boundary over here. And then there's a final term, which is the one that makes the integral non-trivial, which is proportional to the c at this corner, and that involves this max that involves all the t's, and in particular that's sort of their nested sums. Okay, as so. Okay, so then it's just this integral of e to the minus s naught minus s1. Okay. And in particular, from the s naught piece, we just have also the thing that sits in the exponential is linear, and for positive tk, the slope is exactly what I define as being this ak, the variable in my, and the slope along negative t is this linear combination, which is what I define as being bk. Okay, so this is where the variables that I defined earlier are arising, right? Just the sort of slopes in S naught. So already for simplicity, let's consider the case where C star is equal to 0. So we kill off this S1 piece. Then of course, the amplitude just becomes a decoupled integral in all the integration variables and just gives us the simple product of 1 over ak plus 1 over bk from integrating on both sides of the t axis. Okay, so that's what we get. And we'll call this a naught. And so after defining a naught, it's natural to look at the ratio of an over a naught and interpret it as the expectation value of e to the minus s1 under the probability distribution given by e to the minus s naught. Okay, so this is just a way of rephrasing what the amplitude is, this ratio. Okay? And now, from this perspective, we have that each tk itself is just a random variable where the sort of average step size in the positive direction is given by 1 over ak, and the average step size in the negative direction is 1 over bk. Okay? So now the goal to estimate what happens at large n is find a good way to upper or lower bound these an such that the amplitude saturates this bound at large n. Okay? So from this definition, it's clear that a very simple upper bound that we can come up with, since S1 is given by this max and one of the entries of the max is 0, then it's clear that S1 is always greater or equal than 0. And therefore, we have that this expectation value is smaller or equal than 1. And so we already know that if you want a naught itself is a true upper bound for the amplitude. Okay, so this ratio is smaller or equal than 1. And now, a way to find a lower bound is just using Jensen's inequality, which tells since the exponential is a convex function, let us write that this expectation value is greater or equal than e to the minus the expectation value of S1. Okay, so now we managed to upper and lower bound the amplitude. And now we just ask, okay, let's consider some particular kinematical regime, say when all of the AKs are smaller than the BKs. Well, in this case, all of the expectation value of each TK will be greater than 0, because anyway, it's an exponential expression. And therefore, if we look at the form of S1, we see that if each TK is going to want to be positive, so in this max will be mostly dominated by the 0. So therefore, we learn that at least in this kinematical regime, we have that the expectation value of S1 itself is of order 1. Okay, so it does not grow with n, crucially, so it's of order 1. Okay, and then we're done, right? Because we've managed to upper bound by something of order 1, and over here we also have something of order 1, and since a naught itself was already growing exponentially with n, we learned that the way that an behaves with n must exactly match the sort of behavior that a naught has. Okay, and so that was our first result, that the log of an over n asymptote was converging to this log of a naught over n in this particular regime. Okay? But so now let's look at other cases. Say that AK is greater than the BK. Now in this case, all of the TKs will want to be negative. It's the opposite regime. And so now instead this max function will be dominated by the sort of last term, because all the T's are negative. And so instead we have that the expectation value of S1 is now of order n. Right? And so now we learned that actually what we got is a pretty bad upper and lower bound. Right? This guy goes to 0, so we just learned that this ratio is between 0 and 1. So clearly, this is not a good upper bound or lower bound on the amplitude, so we need to do something better. In particular, what we'll see is that there is a much simpler and much a much more natural upper bound that we could have come up with than what we did before. So originally we said, well, in this max there's an entry which is 0, so it's clearly that the max is greater or equal than 0. But in general, if I have a max with different entries, I can say that it's always greater or equal than any weighted average of its entries, right? Where these weights have to add up to 1. Okay?
The weights are positive?
The weights are positive and have to add up to 1. So they're all between 0 and 1. Okay, so anyway, so this is another upper bound that I can use. So using that, if I plug that, so if I replace my complicated max in the integral defining the amplitude by this upper bound in terms of the weight, I've managed to, again, fully decouple all of my different integration variables in this upper bound, and all that this is really doing is sort of redefining the AKs and the BKs that entered in S naught. So that now this new sort of result that I get is the same decoupled product where now the AKs and the BKs are shifted by C star times sigma k, where these sigma k's are basically the consecutive sums of the weights. Okay, such that since the weights themselves have to be between 0 and 1 and positive, the sigma k's have to now be ordered and also live between 0 and 1. Okay? Anyway, so this is my new upper bound. Now this upper bound is a function of sigma itself, and for any value of sigma that lives inside this domain, it is a valid upper bound. So the thing we want to do is, given some kinematics that define some profile of AK, BK, and C star, we want to ask what's the choice of these sigma k's that gives the best possible upper bound, or in other words, that minimizes this A naught of sigma. Okay, and the bonus that we'll see is that it turns out that the amplitude saturates this best possible upper bound at large n. Okay, so I will not prove this now. This is all proven by the sort of dual theory that I'll describe at the end. Okay, so the first thing that we can ask is what is directly the minimum of this A naught of sigma? And since each sigma k only appears in one factor in this product, that's an easy question to answer. And it turns out that the minimum happens for a value that I'll call sigma k star that effectively makes the A tilde k equal to the B tilde k. So it's a situation where they're fully balanced, like sort of these two numbers are exactly the same. So it's this funny ratio that I also introduced a little bit earlier. But now, of course, depending on the values of AK, and BK, the sigma star k can live inside the domain or outside, right? So the minimum of this A naught of sigma might live inside the domain, or if it lives outside, then the best thing that we can do is pick some sigma k's that live at the boundary of this domain. Okay.
Can I ask a question?
Mm-hmm.
Is there some intuition behind this answer by understanding the shape of the Feynman diagram in terms of Schwinger parameter that dominate in a larger limit?
Yeah, I would say under this assumption of these smooth kinematics, it's not obvious that there's a class of diagrams that it's dominating. So that's really in the sense in which it is like you're sort of you're smoothing out the whole sum. It is true that, as we saw before in the like sort of previous case, where if all the t's want to be negative, then you are going to be sort of restricted to the domain of linearity of that max that kind of is a particular subset of your space, which is picking out the contribution from some particular subset of diagrams, indeed. But in general, it's not, you see, that analysis is not always as linear. So that's why with these weights, then it's a little bit harder to sort of track to which exact region are you sort of going back to. Okay, so let's now, in this language, sort of rephrase exactly the previous case. So if AK is smaller than the BK, we have that this sort of location of the minimum smaller for all k. So then the best possible thing we can do inside the domain is to set all of our sigma k's to 0. As that's the closest we can be to that regime. Anyway, and so we see that when we do that, we precisely get the formula that we had before. Okay? But now we can ask what happens in other regimes. So let's say that all of the AKs are greater than the BKs, and now the sigma star k is greater than 1, so our kinematics curve takes a form that looks like this. Then the best thing we can do is put all sigma k's to 1, and then we land on this other formula for the asymptotic behavior. And anyway, so here's some numerics sort of showing a regime like that. Now, the sort of another case that we can study is what we call this tracking case, which is a situation where the kinematics curve lives within the region that we're allowed to access inside the domain. And so that means that the best thing that we can do is pick all the sigma k's to equal the sigma star k. And so if we do that, we get this other simple product that I also showed earlier. And in particular, this is the kinematic region that lets you access the zero-dimensional limit, where you're just counting diagrams, and that corresponds to putting all of the AKs to 1 and the BKs all to 0. And so from here, you precisely see the sort of emergence of these 4 to the n, which is these Catalan asymptotics, just counting the number of diagrams. Anyway, so here's an example. We pick some profile. Of course, in the region where they go beneath 0 or above 1, the best thing that we can do is keep the sigmas at 0 or at 1. And here's again the sort of comparison with the numerical result. Anyway, now there are other interesting cases, like say that the sigma star k is actually decreasing with k. Then since our sigmas need to be increasing, the sort of best possible thing that I can go is sort of look at the limit where they all become exactly the same. Right? And now if they all become exactly the same, the best possible upper bound is the one where I say, well, I vary over this sigma bar and ask which value of sigma bar makes this a naught of sigma a minimum. Okay, and that's equivalent to this sort of equation that I wrote down earlier. Okay, but here I cannot give you the sort of closed form expression. You would need to find the minimum for the particular kinematical profile that you have. Anyway, so here's an example that I also showed earlier, right? This is the optimal value of sigma bar and the comparison. Anyway, but now that you have all of these different ingredients, given some kinematics, you plot down what are these profile for this quantity sigma star k, which in general might take some form of some curve. And then at each step, it's clear what you have to do with your sigmas. So when the curve is beneath 0, the best thing you can do is stay at 0. When it's increasing, then you should track as you can. But now since this curve sort of inflects and turns down, then it's clear I can't track it forever. Eventually, I'll have to switch into a constant. And then when it starts increasing again, I can track again, and then eventually stay at 1. Right? And so by looking at solutions that look like this, now to find the minimum, I have to vary over this parameter k star and find what's the value of k star that gives me the best possible upper bound. Okay? Anyway, so here's an example of some underlying curve for this quantity, and this is what we found as to be the best sigma k for the upper bound. Okay, but so the summary of this part is that we have that the amplitude for this theory at asymptotically in large n is given by this interesting optimization problem. Is this minimum of this function where the sigmas live inside this particular domain. Okay, and the interesting aspect about this is that the complexity of this optimization problem does not really grow with n. Under this assumption of smooth kinematics, once you specify the curve or the function from which you're reading off the kinematics, you have some function that will have a certain number of bumps, right? And that's the thing that determines the complexity of the optimization problem. If you increase n, that will not make the problem more complicated, okay? So this is a sense in which the smooth kinematics is crucial. If it was completely random, then that would not be the case. Okay, so actually I don't have, there's a clock there. Okay, sorry, so I have 7 more minutes. And anyway, so I'll just go through now this last part of the sort of dual theory. And so the main idea is the following. Already having the previous integral, one natural question you can ask is, well, can you interpret this as some sort of path integral in this t space, say? And already something which is very annoying is the fact that it has this max function, which is extremely non-local in the t's, right? To sort of know what it evaluates to, I need to know something about all the different t's. And so what we do is there's a few manipulations that basically turn this integral into a one higher dimensional integral that turns it into something completely local in a new space, okay? And so this is what I'll describe now. And now this new integral has this interpretation of describing the motion of a particle on a half line. So let me show you what the integral looks like. So it's now an n-2 dimensional integral in this tau space where differences of adjacent taus are the things that previously we called t's, okay? And it has this piece over here, which is exactly sort of giving you the total length of a path in tau space. If you draw some particular path in tau space, this is giving you a sort of total length of this path with some interesting sort of metric factors if you want at each step. So if all of the gamma k's were the same, then it would be literally a length. These gamma k's are in turn the things that sort of capture the kinematics in the integral. And then on top of that part, there is this further factor basically which tells you that the center of mass of the full path cannot be very deep for large tau. This factor is crucial otherwise because this integral, this translational invariant, it would diverge as tau goes to infinity. Okay, so this is what the integral looks like, but crucially, it's fully local in tau space in the sense that each tau only sort of talks to its adjacent neighbor. Okay? Anyway, and as you project down in 1 dimension, this is just sort of a walk in a one-dimensional space where it always stays above the 0 because all the taus are positive, are integrated over the positive axis. And in this picture, n is then the sort of total number of steps that you've taken. Okay? Anyway, so let's see in this particular picture, how do we obtain or get back the picture of diagrams, or the sort of way in which, what does a given diagram corresponds to. So one natural way of dividing all the possible paths into subsets is by listing the position at which a given path reaches a minimum. Right? If a path has a minimum at some position k star, then the path on the right and the path on the left are exactly of the same form as the original path. So summing over all the possible paths on the left and on the right precisely sort of gives you the two lower point amplitudes. Okay, so anyway, so if you divide the space into the location where tau k star is the minimum, then you precisely divide the amplitude into the sort of all possible products of lower point amplitudes, and that's exactly the picture of these sort of recursion relations. And so if you keep iterating this process, it's clear that eventually you'll land on a diagram, and so the diagram is just given by some particular region in tau space. Okay, so this can be easily read directly from the graph, but just to see an example, it's some particular chunk of this tau space. Okay, so, but the crucial sort of point to emphasize is that a diagram is something pretty global. In a sense, we need to know some particular ordering of all taus, and it builds up the whole answer by adding up all the different regions. It divides the space into chunks, and you need to add up everything to get the full amplitude. And so this is why it's hard to, from here, extract what happens at very large n. But instead, when you're given this particular representation of the amplitude, there's a much more natural way to approach the integral, which is just by asking what happens when you integrate out the last step. Okay, sort of the analog of what time evolution would look like. So this is, and precisely because the integral is local in tau space, when you integrate out the last one, you get some factor and a function that depends on just the previous tau, right? And so in this way, you're building up the full answer in a more multiplicative way. And that's why the large n limit is sort of made obvious. Okay, so one kind of curious fact that we learned from this picture is that, for example, in the regime where the AKs are smaller than the BKs, the typical path looks something like this. And using this picture, we can now predict that on top of the asymptotic behavior that I showed earlier, there's some correction that depends on the kinematics kind of at the end of the path. But then it turns out that all of the corrections that come from changing the kinematics at the beginning are non-perturbative in n. Okay, so they're exponentially small in n. Okay, so that's quite surprising, and the original picture doesn't make it obvious at all, and it's all sort of a consequence of this locality in this tau space, one higher dimensional space. Anyway, but so the way to approach solving this integral is by asking sort of the standard transfer matrix description. Just ask what happens. What is this sort of the operator that corresponds to doing one-time step, right? So this is some integral transform that depends on these gamma k's, takes some function of tau prime and spits out a function of tau. Anyways, this operator over here. And then once you know the operator, you can ask what are the possible eigenfunctions and the respective eigenvalues. And so basically knowing the spectrum. And so when you have that, then you can really just fully evaluate the integral. So in a simpler case where all of the AKs and the BKs are equal, just for simplicity, the amplitude is really just given by this Euclidean transition amplitude, where you've just acted many times with this time evolution operator. And so eventually you're just basically going to converge to the largest eigenvalue of this operator, right? Because you're sort of acting with so like large n corresponds with acting with this operator many times. Okay? So anyway, in particular, if you do that here, after you decompose into the eigenfunctions, you find that the overall prefactor already has the correct sort of asymptotic behavior that we derived earlier, and then you're left with some integral in this frequency space for these eigenfunctions. And from here, by performing some simple saddle point analysis, you can derive the sort of further 1/n corrections. So this n to the 3/2 that we had already for these Catalan numbers. Anyway, but in general, if you study the completely general kinematics, where you have so generic AK and BK, this is the general form that this operator takes. And you can just, again, analyze its spectrum and ask what happens. So in particular, the case that I was just looking at was when the A tilde were equal to the B tilde. So in this case, all the eigenvalues sort of form a continuum. And there's the biggest one, which is the one that is sort of dominates at large n when you apply this operator many, many times. And precisely because there's no gap, all of the corrections are power law corrections. But as you move around kinematic space, so for example, if you make A tilde k different than the B tilde k, you notice that there's a gap that opens, and now the sort of biggest eigenvalue is exactly of the form that we sort of had before. And this one is the one that sort of dominates at large n, and in particular, because of the gap, there are exponentially small corrections to this linear behavior. Anyway, so I'm going to end now, and so just ending with some general remarks and outlook. So, of course, if you really want to understand the full systematic 1/n corrections, one thing you need to know is, I said we neglected all of the internal C's because they were ordered 1/n squared. Turns out that at leading order in n, we know how to include them. In certain regimes, they really don't matter, like in this case, but there are others where they do matter. And so instead of sifting by just the C star, there's some more interesting sums of these C's that give you the asymptotic expansion. But again, we still don't know what the analog of this tool theory that I described is in the case where you have all of the C's sort of turned on. The thing that we do know is that there also is a sort of one higher dimensional integral which sort of generalizes the one that I told you before, where instead of it being fully, where it being fully local in tau space in the sense that each tau only talks to its adjacent one, now each tau is compared to a string of taus that sort of depend on the particular kinematical indices. Okay, so this is an integral that gives you the full amplitude for any kinematics. This is something we're still analyzing.
It's a strings theory, not a particle theory.
Well, yeah, we don't. Anyway, we still don't know exactly like how to extract, for example, the large n behavior from here, at least in the most general cases. Anyway, this thing that I hinted at the beginning, there's a simple kinematic deformation that allows you to take the trace phi cubed amplitude and obtain the pion amplitude, which is just deforming these xij's in a way and taking a particular limit. And it turns out that this shift interacts with these large n asymptotics in a predictable way, such that we can use the formulas for this trace phi cubed theory at large n to write similar ones for pions at large n. So anyway, I don't have time to go much into this, but it's just so you know. And ultimately, all of this also generalizes to the context of open strings at large n and also at high energies compared to 1/alpha prime. So in that case, all that you do is you start out with your optimization problem that we had for the field theory. We replace this sort of 4-point factor by the analog 4-point amplitude in string theory, the Veneziano amplitude, and then you extract the high energy limit of this guy, and we claim that the optimization value problem for this function is now what gives you strings at high energies and large n. Okay, I'm sorry, I don't know why I have these drawings here, but the future directions that we definitely still want to explore is what happens for completely general kinematics. This connection that connects scalars to pions also extends to gluons, so it'd be interesting if we could say something about that. And of course, going beyond tree level, thinking about what happens at large loops is also something that we're thinking about. Okay, thank you so much.
Beyond tree level, you expect this dual picture still hold?
At one loop, it seems very likely that it will hold, just because the integrals that we have, these global Schwinger representation, look very, very similar at one loop. At higher loops, there's some subtleties associated with the sort of mapping class group. All of these integrals come from a surface, and anyway, so there's a few more subtleties, like starting at 2 loops on. We've not looked at it explicitly, so I don't know how much we'll be able to say.
Most likely when the number of loops is small, is called fixed, and little n increases, essentially nothing happens. I think we expect the formulas are likely just unaltered. Something interesting happens when little n and L start becoming comparable, of course. And if you like, most of the non-perturbative things we know, even in low dimensions, matrix models, and so on, are very small n and L huge. So somehow the really interesting, well, Carolina referred to it early in the talk, the really interesting question is, even in 0 dimensions, I mean, is sort of melding these two worlds together, understanding what happens at large L and large N at the same time. But it's pretty clear from the structure of all these integrals that low loop will not really interact much, but it won't change the story really.
Because you can kind of decouple the like loop part from the tree part. Like in all of these integrals, anyway, this should not be very intuitive, but that's basically the reason. Like the complication of large loop is saying already for a tadpole, can you do the like tadpole at like large number of loops? If you can do that, then adding many more legs will not sort of make the story much more complicated. That's sort of what we expect.
Yeah, because coming back to what Valery was doing, there of course the motivation was that as n gets large, this three-level amplitude starts violating unitarity.
Yes.
And that was semi-classics to calculate. Which was
Here we don't have
producing
that feature, of course. So here we don't have that feature because it's power law growth and not factorial growth. So that's another difference
Yeah,
between
that,
the
yes,
two of them.
between the uncolored and the colored case. Yes.
That's why there's a hope this is somehow, I mean, just to go back to the motivation, one of the very early slides, the hope is that this dual theory we're seeing is the beginning of the string theory, but the beginning of the string theory at like, at large N rather than at large L. Okay, so somehow if you crank up, I mean, after all, just what she said, if you have 2 to N scattering at large coupling, you're making strings. I mean, you're making some surface, some flux tube, something like that. So you want to vividly see the stringy object you're making, whatever the heck it is. It's not kind of a free string, obviously, but whatever the heck it is, the flux tube, whatever it is. You're going to see it in 2 to N. You're not going to see it in 2 to 2. We see it super indirectly in 2 to 2 because, you know, we know that the amplitude is some area minimal surface, ADS, but that's a highly theorist-dependent thing. The actual amplitude is exponentially small, and you have to be very smart to know to interpret that exponent as the area of some surface in the ADS. What really happens mostly is that you produce a humongous number of things in the final state that kind of organize themselves into some stringy thing that we don't quite know how to think about. The fact that there's some regime where something simplifies at large N, that's, I think, the most interesting thing about it, is that there's a dual theory at any N, but it simplifies at large N, is what we're so excited about, right? Because somehow it feels like that's the beginning of the structure that, as you crank up the coupling constant, will actually turn into the, turn into the living string at finite coupling. But none of that would be true in the uncolored theory. So somehow, that's also precisely why you expect something nice to happen in infinite color. The nice string is going to emerge in infinite color and then have towers of corrections.
But how dependent is on the story on the phi cube interaction instead of phi to the 4th or phi to the n?
Well, at the moment we don't know how to do like phi to the 4th. That's the main thing. We expect that it might also work there, but with the tools that we have to sort of let us even understand, have these integrals from which you can capture all of the diagrams, that is something that we know for phi cube. You can of course decorate them to cancel some of the singularities, to turn them into something that has quartic interactions. But the decorations that we know how to do, like at the moment, are a little bit artificial. They're not like, they don't let us see how all of this generalizes there.
What's amusing though is that precisely the theories that this kind of thinking, forget the large N story, just the pre-story, they're good for theories that are somehow canonical. If you say phi to the 4th theory, it's not canonical. You have to make a choice of what you mean by the phi to the 4 interaction. Is it a constant? Is it derivatives? What is it? Phi cube, there's nothing you can do. There's one coupling. And so it's funny that it's not too canonical to get phi to the 4, but there's this trivial deformation that gives you pions. I mean, I care more about pions than phi to the 4. Pions exist. Colored phi to the 4th, less so. So it is. So that's not so obvious that it should be the case. But that's a sort of a pre-story here, that there are these families of theories that we care about that end up being essentially identical when you look at them the right way.
Any other questions? Thank you.